You got it? Okay. We'll begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I just thank you that you loved us and you came to earth to die for us, and we just accept you into our hearts. We have forgiveness of our sins, Lord. We thank you for that. I just ask that you would bless this class today, help us to enjoy the math as we do it, and help us all learn what we need to today. Again, I pray that the students would have courage to ask good questions as they occur to them. In your name I pray, Lord Jesus. Amen. All right, so let's talk a little bit about the geometry of complex numbers. So we basically, last time I showed you a fair amount about the algebra of complex numbers. Now I'm going to start more with the geometry of C. So here's the fundamental picture, right? We can identify the complex. We're taking the viewpoint that the complex numbers is essentially R2, but it's R2 with a special notation, if you like. It's A plus IB, such that A and B are real numbers, right? And so if you pick any point in the complex plane, so this is usually called the real axis, this is the imaginary axis. So if I pick a point, like say here, that point we could call, say, Z, and it could be x plus IY, right? And as usual, when I'm thinking about the plane, well, just more generally, Rn, I have a choice, right? I can either think of the points as points, whatever that is, or I can think about them as directed line segments from the origin, right? I can think of them as vectors. And we have this interchange between these two concepts, right? So we'll freely make that identification, but with that said, there's a natural, you can think of complex numbers as vectors in the plane, right? So there it is. And of course, in tune with that, we could think about the standard angle, theta, right? Theta would be there. And what's the relation then between x, y, and z? Now last time, we defined the modulus of z. Well, maybe I didn't, but I'm going to define it now if I didn't already. The modulus of z, right, is the length of z as a vector. It is, in fact, the square root of x squared plus y squared. But we do have a purely complex formula for it as well. I would remind you that we can also view it, and we do often view it, as the square root of z bar. Or z bar z, you take your pick, where z bar is the complex conjugate. Okay, so that's the magnitude of this as a vector, right? But if you look at this, then of course we have, we have an x component, we have a y component. So this bit right here would be what? This would be x, right? But we can also write that as the modulus of z times what? Cosine theta. Yeah, cosine theta, right? And the vertical piece is what? It's y, right, modulus of z sine theta. However, if I want to view this, if I want to think of this as being, to be more, I don't really just want to think about the scalar components. I want to think about the vector components. Sorry, Michael. I'm bringing you back to that unpleasant class you were just mentioning. Yeah, I know, but it's okay. It's just two-dimensional in here, so it's okay. This is the x vector component of z. We were doing Calc 3. Right? And the vertical piece is what? It's not y, right? This is actually iy, right? So let me add an I here and here. So if you think about tip-to-tail vector addition, we immediately have the following formula. Z is equal to absolute value, modulus of z times cosine theta plus I modulus of z sine theta. So I can write this a little bit different. Let me just point out that you could just as well write that modulus of z, big parentheses, cosine theta plus I sine theta. Everybody with me so far? Okay. What if I had another complex number? Say z. Oh, say z. That seems like a bad choice. How about w? And let's let w equal to, I don't know, whatever you like. How about, a plus bi, or a plus ib? I don't really care if you write the I to the right or the left. For us, it's, I think it's the same. But, I can do the same song and dance to that one, I can talk about a different angle, let's call it beta, right? And through the same argument, I can come to the formula that z is equal to the w is equal to the modulus of w times what? Times cosine of beta plus I sine beta. And through the magic of, well, it's not really magic, but through the well-constructed concept of the standard angle, this makes sense in all four quadrants, right? Because the signs, SIGNs of sine and cosine are so chosen as to make these formulas extend from right triangle trigonometry to all the plus and minusness that comes with all four quadrants. I'm not sure plus and minusness is really a word. But anyway, you know what I meant, so I guess it is. So there it is. Now what happens if we multiply ZW? So what I'm going to do is factor out the modulus. So I'm not sure, Michael, but this might be the time. Let's see here. Your goal, your basic goal in taping here is to be better than Belu. So she might be watching this, which is what makes it fun to insert comments. Oh, you don't. This is a basic principle of taping lectures for me. No one cares where I am or what I look like. All you care about is what's on the board, you know. So that's the general principle. Okay, let me get back to the complex analysis. So, although we're not quite there yet, are we? All right, so this, you multiply this out, what do you get? Well, remember last time we proved that the modulus of ZW, modulus Z times modulus of W is the modulus of ZW. That is a non-trivial identity, but it is true. Okay? Easiest way to prove that is using the complex conjugate. Now, then on the other hand, the other things we have what? We got cosine theta, cosine beta. I times I is I squared, right? So I get minus sine theta, sine beta, plus I cosine theta, sine beta, plus cosine, plus sine theta, cosine beta, close big brackets. And can you guys tell me anything about that? Yeah, those are adding angle. The adding angles formulas give me a way to simplify that. In fact, that's just what? That's cosine of theta plus beta, right? And I sine of theta plus beta, right? So what happens when we multiply two complex numbers? When we multiply two complex numbers, their new standard angle is the sum of their original standard angles, and their new modulus is just simply, the new magnitude of the complex number is just the product of their magnitudes. So complex numbers, the multiplication of complex numbers has built into it rotations in the plane, right? Which I think is kind of neat. So at this point, we make a definition. Any questions? So if I was to foolishly, I'm not going to try to picture ZW, but it's somewhere over here, and it's, well, I guess it depends on whether this is less than 1, or it really depends on whether we're looking at something, somewhere there's a unit circle here, right? If one of these vectors is inside the unit circle, it shrinks the other. But if they're both outside the circle, the product of their magnitudes is larger, right? I mean, you multiply two numbers. Is it bigger than either of the number, or is it smaller than either of the numbers? It depends on whether one of those numbers is larger than 1. Or that both of those numbers are larger than 1, I should say. So we have a definition, which is that e to the I theta, all right, is equal to cosine theta plus I sine theta. This is sometimes known as Euler's formula. Now, I would say that this is a transitional definition because we'll find a more pure way to come to this idea later in the course. But for now, I think we can think of this at the moment just as a notational convenience, right? Because with this notation, what do we have? we have what? We have, okay, so then z is equal to the modulus of z times e to the I theta, where theta is the standard angle. Right? Now that's by no means unique because theta could be different, right? You say it's pi over 4, I say no, it's pi over 4 plus 20 pi. That's the same thing geometrically, right? But of course pi over 4 and you add your favorite multiple of 2 pi, those are different actual numbers, right? So the choice of theta is by no means unique unless we make a choice, right? And what else do we have? Likewise, w. See that? So what does it look like then? We've got zw is modulus of z e to the I theta, modulus of w, e to the I beta. And what happens when we multiply them? We get modulus of z times w, combining this guy and that guy, right? And we have what? E to the I theta, e to the I beta. But let me just be more to the point. It's really e to the what? E to the I theta plus beta, right? I mean, that's what we proved in the purple. So what we have is something really neat. We have a law of exponents for this so-called imaginary exponential. I think the term imaginary exponential pretty much explains itself, right? And so what we have here, again, is e to the I theta, e to the I beta is equal to e to the I theta plus beta. So, I mean, calling it an exponential is a very reasonable notation, right? Because, in fact, it does behave like an exponential. It has the exponential law, right? What else do we know about exponentials? What should 1 over an exponential be? Conjugate? I mean, I guess, okay, so, oh, you're right. But that wasn't, not the answer I was expecting, but my point was, usually we can, you do what? I mean, this should be e to the minus I theta, right? But once you know this, that's pretty much automatically the case, right? Because what, e to the I theta, e to the minus I theta, I get e to the I theta minus I theta, which is e to the 0. Of course, this begs a question, right? Is this consistent with the real exponential? In the case, what case would you have to worry about? Where would it have to be consistent with the real exponential for this notation not to be really suspect? When can cosine theta plus I sine theta be a real quantity? What do you have to have? You have to have sine theta is what? 0, right? So sine theta would be 0 when theta is a multiple of pi, an integer multiple of pi. And if theta is an integer multiple of pi, you've got cosine theta is, well, I suppose you have, oh yeah, I've got cosine theta is plus or minus 1. Interesting. Well, I guess we have, there is something new here, right? Let me stop talking to myself and show you what I'm saying. So on the one hand, we have like e to the I pi, and I'm trying to think here. Oh, it's always, 0 is the, or you can think about things like e to the 0, or 0 times I, right? Or e to the 2 pi I, just to give you a sense of what I'm saying. E to the I pi is something people like to talk about. That's cosine of pi, right? Plus I sine of pi, which is 0. So that's minus 1. So e to the I pi is equal to minus 1. E to the 0 is cosine of 0 plus I times the sine of 0, which is just what? 1, right? So that's also the exponent, if you'll let me use this notation for a second. It's also the exponential of 0 if you think of exponential denoting the ordinary real exponential you study in calculus, right? If I had something different for 0, what is it? Oh.
I'm drawing a sine wave.
Oh, okay. I'm in your head. I mean, I could see it, so let's see here. Sorry. I'm easily distracted, as is well known. So, there's no danger for the notation. It agrees with the real exponential in as much as it can compare. In fact, let's get to the point here. I theta is only real when? When is I theta real? There's only one theta that makes that real. 0, right? Now, if you ask me when is e to the I theta real, there is infinitely many theta that does that. I asked the question, when is I theta real? Theta equals to 0. When is e to the I theta real? In other words, if you ask me the question, e to the I theta, and how would you capture reality of e to the I theta, by the way? How would we do that? What does it mean for a complex number to be real? What does it mean for a complex number to be pure? Right. So I would point out that to get reality, you can just have the equation z is equal to z conjugate. To have pure imaginary, you have the equation z is equal to minus z conjugate. So this is real. This is pure imaginary. Those are you could take those as definitions if you like, but they agree with what you guys were thinking about. The real part is the only part that's non-zero. The imaginary part's 0, or the real part's 0. So if we look at the equation, e to the I theta equals e to the minus I theta, which would be, by the way, you're like, wait a minute. You didn't. How do you know that that's the conjugate? Let's work it out. So this is cosine theta plus I sine theta conjugate, right? Conjugate just means you change I to minus I, right? And that is, in fact, e to the minus I theta. Okay, so how do you solve an equation like this? Let me ask a more general question instead of that one. Well, I think I'm getting off track here. So any ideas? I'm thinking about my life.
Could we use logarithms?
What? Oh, but yeah.
First?
Once we understand what the logarithm is, we could do that, but we don't know that yet. Because remember, e to the I theta is a complex value. We have not yet introduced the complex logarithm.
Well, what better time?
We're getting there. But my point to you is, since the exponential, right, the imaginary exponential is built from sine and cosine, it suffers the same degeneracies that sine and cosine suffer, right? If I tell you cosine of theta 1 is equal to cosine of theta 2, you don't get to say theta 1 equals theta 2, right? All you can be sure is that they're 2 pi, some integer multiple of 2 pi separated those values. But thankfully, we have the same degeneracy in both the real and the imaginary part of the definition of the imaginary cosine, right? So in short, we have this general principle, or proposition, whatever you want to call it, e to the I theta equals to e to the I beta, if and only if, let's say, theta is equal to beta plus 2 pi k for some k in the integers. So when you're solving equations involving imaginary exponentials, we have to deal with this degeneracy. We'll generally get infinitely many solutions, right? So coming back to attacking the question of, when is e to the I theta real? So I wanted to solve the equation, what? E to the I theta equals to e to the minus I theta. What do we need? That's going to only be true if what? If theta and sometimes it's, I sometimes think about it this way, but what's another way, an equivalent way you could characterize it? Sometimes it's easier to think about this as follows. Theta minus beta is equal to 2 pi k. Or here's even a better way to say it. Theta minus beta is an element of 2 pi z. I'm introducing some notation there. What does 2 pi times a set mean? It's the set with everything in it, element-wise, just multiplied by 2 pi. So like 2 pi times the integers is 0, plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, plus or minus 8 pi, so forth. It's a nice language. So what we have then, here's what we have to figure out. We'd have what? Theta minus theta is an element of, 2 pi z. In other words, 2 theta, oh man, I've done something askew. No. Well, 2 theta is equal to 2 pi k for some k in the integers. So what are the solutions? Theta is equal to what? Yeah, pi k. Well, of course. Yeah. Oh, I know the thing that's bugging. The thing that is bugging me, it's like I keep thinking, but the exponential can't be minus 1. Where does that thought come from? No, it comes from pre-calculus, where I was taught, where it was drilled into me that exponentials are positive, right? What's the graph of the exponential look like? It has, right, it hits 1 when you put in 0, and you solve e to the x equal to 0. Is there a solution? No, so it has to stay above the axis, right? It's never 0. Actually, that's still true. The complex exponential is also never 0, but I haven't defined the complex exponential just yet. So anyway, that's it, just multiples of pi, because of course, in retrospect, that should have been obvious to us from the start, and probably it was to some of you, because sine of an integer multiple of pi is 0, so for this to be real, I just need the cosine part. Okay, but I wanted to show you how to think about that systematically in terms of the properties of the imaginary exponential. All right, so I have almost defined for you the polar form of a complex number. This is an example of the polar representation of a complex number, right? Oh, sorry. You with me? Okay. So this is an example of the polar representation of the complex number. The modulus we've already defined. The other thing we have to define is the so-called argument, right? So what's the argument? Here. It's the angle, right? Which angle, though? I mean, this, right, is also equal to the one we're referring to. I see what you did there. Okay. Theta plus 2 pi k. I mean, you see, these are equal, right? So which theta? I mean, is it this theta or is it this theta, quote unquote? There's a degeneracy, right? So by definition, the arg, little arg of z, is equal to theta plus 2 pi k, such that k is an integer, where theta is implicitly defined by the equation above. Now, you can write that this is equal to the principal argument of z plus 2 pi z, if you like. How do we add sets? We add arg z to each element-wise, right? It's just what you'd expect. And you're like, well, that's great, but I don't understand what argz is either. Oh, fine, I get that. Here's what argz is. Argz, and this is probably going to seem a little circular, but let's just say that argz is equal to theta naught, where z is equal to the modulus of z, e to the I theta naught, and here's where the heart of the definition is just right here. Theta naught is an element of minus pi to pi, where the positive pi is included. This is the principal argument. Okay. This is a standard notation. We need to remember it. Okay. Yes. Yeah, that's important. Knowing me, you might think it's a typo, but not this time. See here. So, give you an example. If we have z is equal to minus 1, or let's say minus, let me make it interesting, minus 42 minus 42i, you can ask what's the modulus, what's the principal? It's the principal argument. So modulus of z, right, is equal to what? The modulus of 42 times minus 1 minus I, right? Which is, by the way, 42 times the modulus of minus 1 minus I. If you're squaring 42 and adding it together, you're doing this the wrong way. You should factor the 42 out. Use properties of the modulus to see that it's 42 times the square root of 2. Okay? Properties of the modulus. Modulus of ZW, modulus of Z1, Z2 is equal to modulus of Z1 times modulus of Z2, but the modulus of a real number is just the real number again, unless the real number is negative, in which case it's the absolute value. So modulus reduces the absolute value for real numbers. Okay, so then if you picture this, right, z is down here somewhere, right? So remember, minus pi, arg, pi, it's somewhere in there. And which one do we include? Less than or equal to pi, right? So a way to think about that, sometimes I think about this picture as something like, I don't know, I start at 0 for whatever reason. So you go 0 and you swing all the way over here to pi, included, right? Or you go like this way and not included, right? So here we're going to minus pi, this way we're going to pi. But, I mean, it is just a standard angle, right? The principal argument is nothing more than a standard angle. Okay? By what I've wrote on the board. So what's the standard angle then of this one? Keeping in mind it's not quite the standard angle you might usually use. It has to be between minus pi and pi. Pi included. Let's see here. So basically for this one, it's just this bit right here, right? So it's like pi over 2 plus pi over 4. I can see that because it happens to be, I chose a nice number, right? So I know that there's 45 degrees, one side or the other, right? For messier complex numbers, of course, you need to use a calculator or something, right? But this angle is the arg. And so what is it? It's, let's see here, 3 pi over 4? Except that's wrong. Why is it wrong? Negative 3 pi over 4. Very good. What's the little arg of z? If I write it in set builder notation, it's minus 3 pi over 4 plus 2 pi k, such that k is an integer. Again, I can express that same set of points in the more efficient notation, which is sometimes nice to use, as minus 3 pi over 4 plus 2 pi z. Two different ways to skin a cat, but either way we have the desired result. I'm sorry, do you like cats? We can make it a dog. Something else cute, I don't know. What's that? A squirrel? What do squirrels do to you? All right, now, okay, so that's the polar form of a complex number. Move along here. We also have what's known as, well, I can't say it right, but Moivres Theorem. What did you say? I'm pretty sure that's also wrong. De Moivres formula, something like that. Sorry, should have hired a French mathematician, or at least a mathematician. Let's see here. So here's a theorem, and it is as follows: e to the I theta raised to the n power is equal to e to the I n theta. All right. Now, oh, I forgot to say something about the arg I was supposed to say, but I'll come back to it in a minute. So how do we prove this? N equals 1, done, right? I mean, there's nothing much to prove except that if we raise something to the first power, by definition, it's what it is again, right? What do we mean when we say e to the I theta squared? Well, let's suppose, let's use induction, right? So suppose e to the I theta squared, I got squared on my brain. E to the I theta raised to the n power is equal to e to the I n theta, right? For some n greater than or equal to 1. Of course, in a whole number, an integer, positive integer. If I look at e to the I theta to the n plus 1, how do we define that? Recursively, right? This is by definition e to the I theta times e to the what? I theta to the n. But by our induction hypothesis, we have that this is e to the I theta times e to the n I n theta, right? And then using the addition law that we derived from right triangle trigonometry, or whatever kind of trigonometry you want to think about it is, anyway, from the adding angles formulas, we have e to the I theta plus n theta, or just to the point, that's e to the I n plus 1 theta, which shows that the identity holds for n plus 1, and therefore, by proof by mathematical induction, we have the Moivres theorem for all n. It's not too hard, right? But what it gets for you in terms of trigonometric identities is very cool. I'll show you the n equals 2 case, but you know, if you look at n equals 3 or something, it's even more impressive. So what does this mean if we do e to the I theta, say squared, is equal to e to the 2I theta? So this is what? This is cosine theta plus I sine theta quantity squared. And you can square that, right? Like usual. Binomial theorem, whatever you want. Cosine squared theta plus 2I sine theta cosine theta minus sine squared theta. But on the flip side, I can expand e to the 2I theta, right? E to the 2I theta, by definition of the imaginary exponential, is cosine 2 theta plus I times the sine of 2 theta. All right, so when are two complex equations equal? Right? When do we have equality here? Right, and this should be familiar to us from Calculus 3. Sorry to bring it up again. Because two vectors are only equal when both their x and y components match up, right? So just that's what's going on here. Here's that. And that has to be equal to this, right? So we have the identity cosine squared minus sine squared is cosine 2 theta, but we also get this identity. Strip off the I, you get that sine of 2 theta is equal to 2 sine theta cosine theta. Two of your favorite identities involving, sine squared and cosine squared. All just from algebra in the imaginary exponential. This is not my preferred method of derivation, though, because it's still kind of indirect, right? If you go looking for an identity for sine squared or something, you have to do this and then see it in there. I mean, it's not my idea, my personally preferred method, but this is a very famous and well-known piece of math, so I should show you. All right. So I think at this point, I should mention, what are the properties of little arg? What are the properties of the argument? Like if I had two complex numbers, and essentially this is more or less built off the discussion we had at the start of class, right? I mean, we're just really adding notation to understand what we did there. But properties of little arg. So arg of the product ZW is equal to the argument of Z plus the argument of W, where the addition of sets is defined in the natural way, right? You just look at all possible sums of the things in the set, right? That is in fact true, all right? However, what is not true is that the argument, the capital Arg, is not generally equal to the argument of Z plus the argument of W. All right? For example, if I have Z like this, right, and if I have W like that, if I take the argument of Z plus the argument of W, I'll get something larger than, why did I put them over here? That's the awkward place to think about it. Let's put them up here. Sorry. So here's my Z and here's my W. Of course, those arguments are going to be between pi over 2 and pi, right? And if you add those together, you get something larger than pi. Therefore, it's not a principal argument. So this identity is not true for the principal argument. But it is true, unless you look at a suitable restriction of the vectors that can go in, the complex numbers that can go into it. In other words, but on the flip side of things is the argument, the little argument, is not a function, right? A function is single valued. If you feed the little argument a complex number, you don't get back a single value. You get a set. It's not double valued. It's not triple valued. It's infinitely many valued. It's very bad. But at the same time, we understand it and we use it. Okay. This was the set of values. They're related in the following way. Little arg of Z is equal to big arg of Z plus 2 pi Z. This is the specific standard angle for Z between minus pi and pi included, the minus pi not included, and little arg is all possible standard angles for Z, basically.
It bothers me that the capital 1 is a value, whereas the small lowercase 1 is that.
Oh, it bothers you that we use the same thing? Well, it could be worse. We could use just one symbol and interchangeably refer to them as both a function and a multiply valued thing. That's what some books do.
Well, no, the issue is, I feel like the function should be the one with the lowercase at the beginning. Yeah. And the set should be the one with capital. The sets are usually capital letters.
Not here. People can't hear what you guys have to repeat your questions. The argument was, since it's capitalized, it should be the set. But in fact, there is no such convention, so sorry. I mean, I guess I don't really have to defend it. I could just say I'm just doing what it says in the book, so deal with it. But I was just trying to, defend the author or whatever. It's just a notation, right? You got to do something. You don't see it in the book? Huh. Oh, so maybe I do have to defend myself. Maybe I do have to defend myself then. All right. So up to this point, I think the things we've done today are pretty elementary, and it's just, in some sense, just a lot of name calling. What I'm about to show you is maybe a little bit more interesting. So definition, suppose n is an integer, positive integer, and w and z are complex numbers such that z to the n is equal to w. Then z is an nth root of w. Moreover, the set of all nth roots is denoted w to the 1 over n. All right, now our default notation, by the way, is that this is in fact not equal to this. The radical symbol there is actually going to be a function, a very specific choice of root. So we're going to make a distinction between these two objects. I know you've been taught to identify them, but now we're going to separate them. We need one notation for the thing which is a set and the other notation for the thing which is a particular object. All right, so let me so this is you're like, well, why are there n roots? Well, let's look at some examples. Let's not look at an example. Let's look at the general problem. So what do these look like? What does this look like actually when you flesh it out, right? So let's let z to the n equal to w. Let's try to see what the form of z has to be. So let's let z equal to rho e to the I theta. So here rho is the modulus and theta is, I don't care, it doesn't have to be the principal argument, it's some argument, all right? Anyway, there it is. So what do we have? We have rho e to the I theta raised to the n power is equal to w, right? But let's see, that's rho to the n, e to the what? E to the I n theta by Moivres theorem equals to w, right? But let me write w out a little bit more specifically. W is equal to the modulus of w times e to the, I don't know, let's just be specific, I arg of w. That's just a choice on my part. How do you solve such an equation? You have two vectors written in terms of their magnitude and direction. The direction is actually given by the imaginary exponential. The magnitude, well, is the modulus. So the moduli have to match and the directions have to match, right? So this actually gives us two equations. We have, on the one hand, rho to the n is equal to the modulus of w. And on the other hand, we have the more subtle equation, e to the I n theta is equal to e to the I arg, capital Arg, of w. So the first one I can solve just standard, algebra from our study of real algebra before. This is rho is equal to the real nth root. Sorry. See, this is the unfortunate thing, is there's just only so many symbols to go around. It is also our custom to understand that if we take the nth root of a real number, it is in fact the traditional nth root of a real number. Actually, there's no ambiguity because they'll match up. when we define this nth root for a complex quantity later, okay? So there it is. You take the nth root of the modulus to get rho. And on the other hand, over here, what do we have? We've got n theta is equal to arg w plus 2 pi k for some k in the integers, right? Or more to the point, theta is what? Theta is equal to arg of w plus 2 pi k all divided by n for some integer k. So what I've done is just prove a little theorem. I'm not sure it's really a theorem, but here it is. The nth roots of w is equal to the set containing elements of the form nth roots of the modulus of w times e to the I parentheses arg w plus 2 pi k divided by n, such that k is an integer. Now, I can actually rewrite this a little bit better as follows. I can say, well, that's really the nth root to w times e to the I capital arg of w divided by n times e to the 2 pi I k over n, such that k is an element of z. Now, the reason I might want to do that is because the thing I'm about to circle in red is a very important quantity. This is what's known as an nth root of unity. What's unity? 1. Good. Good. So if I call this thing, I guess I'll call it omega sub n. If you raise that to the nth power, what happens? Yeah, the n's cancel, right, by de Moivres theorem again? Or an suitable, no, it's de Moivres theorem. And then e to the 2 pi I k is, as we talked about earlier today, it's one of the real values. In fact, that's where cosine is 1. So that's just 1. So as you can see, that omega n is an element of 1 to the 1 over n. It's just one of the nth roots of 1. See, so to find the set of n roots, all you got to do is find one of them, and then you can just basically multiply by these nth roots of unity to create the whole set of roots. Let me show you an example, and then we'll stop for today. For example, suppose we want to find the fourth roots of, give me something that's the fourth, how about 81? 81 is 3 to the fourth, right? Let's make our life easy. So let's find the fourth roots of 81, and I'll say 81i. Find the fourth roots of that. So supposedly this is going to be, let's see here, I is what? E to the what? I pi over 2, right? So if this is, if this is w, you can see that the arg of w is pi over 2. So what I have then is I have, 81 to the 1/4 e to the I pi over 2, sorry, e to the I pi over 2 times 4, and then omega sub 4. Well, omega sub 4 to the k. Oh, I'm sorry, it's not, goodness gracious. Trying to connect with what I wrote over here, you know. So at the moment I've just wrote the first term and the second term. Here n is equal to 4, so I really have e to the pi I over 8, right? And then I've got these terms, e to the 2 pi I k. But I really wanted to look at it as e to the 2 pi I over 4 raised to the n, not to the n, to the k power, such that k is equal to what? 1, 2, 3. Oh, sorry, k is an integer, right? It could take all values, right? I mean, that's what the math led us to start with. It does simplify, though. That's part of my point of this example. This actually, if you start tracing out what it really is, what is e to the 2 pi I over 4? I kind of just discovered it over here. That's e to the pi over 2, which is just I. So this is I. And what's I to the k? So you've got I squared, I cubed, I to the 4th, and so forth, right? That actually loops back again, right? Because you get I, minus 1, minus I, 1, I, and it just keeps going and going and going. So actually, when you tilt your head and squint and really think about what this is, there's only 4 values in this thing. That's not an accident. The nth roots will only have n distinct things. So this here, getting to the point, is 3 e to the, what is this? Tell you, I'm just going to go ahead and save myself from writing up. Factor this 3. I can pull this is 3 e to the I pi over 8. And my roots of unity here are just I minus 1 minus I and 1. Right. Or you know, if you want me to suffer the writing of everything, so that's 3i e to the pi I over 8 minus 3e to the I pi over 8 minus I times 3e to the I pi over 8, and then finally just 3e to the I pi over 8. If I remember right, the one of these which is based on just using 1 is, I think, the one we call, I mean, I'm a little bit rusty on this, but I think this may be, this last one may actually be the, if I had to guess, I think this is what we called the 4th root of 81i. Anyway, as we're discussing complex variables, we have to face these degeneracies. I mean, it's just the nature of the beast. And it is part of what makes the topic difficult, but if we're aware of the issue, it's not too hard. So, anyway, I will shut up for today. I think I'm out of time, probably. Oh, I'm sorry.